Okay, in this video we are going to finish section 6-6, the inverse trig functions. This is our third day on this section, and we're going to tackle this last bullet point. We're going to evaluate and graph compositions of trigonometric functions. Well, actually, I don't think we don't graph any of them, but we're going to evaluate these composed trig functions. And let's just do a little review here. Earlier in the year, we did a previous chapter, I think it was chapter 2, section 7, about inverse functions. And we have f is the function, and f, that -1, is not really an exponent. That's telling us that that's the inverse function of f. And they contain these properties. And let's do a little quick example here, a nice easy one. If I have x, let me back that up. If I have x squared, and I square root it, that is a function and its inverse. The squaring function does one thing. The square rooting function undoes what the squaring function did. So when we did these in class, I would say that the square and the square root cancel, so they wipe each other out, and our answer is x. We could also reverse that. We could take the square root of x, that's one function, and we could take that square root of x and square it. And the square root again will cancel, and our answer will be x, what was under the radical. The square and the square root, one undoes what the other did. And that's what this notation says, but it's just more abstract, and it can be extrapolated to any function and its inverse. If we're taking f of the f inverse, this function and its inverse function will cancel, and we're left with x. The same thing if we do the inverse function first. Here we were doing f of f inverse. Now we're doing f inverse of f of x. The f of x, or the f and the f inverse, the f and the f inverse cancel. So we're just left with the x. Okay, so that's just, a quick review. What are composed functions? One function that's run through another. And if they happen to be inverse functions, they're going to undo what the other did, and our answer in this case is just going to be that x. So let's talk about these when we relate them to the inverse trig functions. So the first one says, if x is between 1 and -1, and y is an angle between positive and -1/2 pi, then the sine of the arcsine of x will equal x. And also the arcsine of the sine of angle y is equal to y. So let's see what's going on here. First, sine is on the outside, arcsine is on the inside. As long as this x value is between 1 and -1, the sine and the arcsine will cancel out, and our answer is simply x. Alternately, if we have arcsine first and sine is the inner function, as long as this angle y is between positive and -1/2 pi, sine and arcsine will cancel, and our answer is just y. Let me back this up. This might hopefully clear a little confusion. If we're doing the sine of something, we take the sine, and we take the sine of, in the parentheses, is an angle. I'm just going to use pi over 2 as an example. The sine of an angle is equal to a number, and the sine of pi over 2 is equal to 1. So for sine, we put angles into sine, and out comes some number, some value. If I do the inverse, the sine inverse, or the arcsine of a number, I'm taking the arcsine of a number, out pops an angle, pi over 2. So angles go into sine and numbers come out. Numbers go into sine inverse and out comes the answer as an angle. So that's what's going on here. Our outer function is sine. What comes out of here is going to be some number. This arcsine of x, that's going to be an angle. That angle will go into sine, and out will pop the answer, and in this case, it's going to be x. And here, we're taking the sine of something, so in these parentheses, that's going to be a number. That number is going to go into arcsine, and out of arcsine will come some angle. Remember, this value y is some angle between positive and -1/2 pi. Now let's look down at arc cos. It starts out the same. If x is a number between 1 and -1, and y is some angle between 0 and pi. Now let's back up a bit. Here's quadrant 1, 2, 3, 4. In day 1 of this section, we learned that arcsine is only defined in quadrants 1 or 2. from up here at positive half pi down here to negative a half pi. We can only do angles in here, and we can't do angles that open up and spread out through quadrants 2 or 3 where arcsine is not defined. When yesterday, in the previous day, when we did arc-cos, we learned that arc-cos is only defined in quadrants 1 and 2. So for arc-cos, our angle y has to be an angle between 0 and pi. If x is between 1 and negative 1, and y is an angle between 0 and pi, then these hold true. The cos of the arc-cos is that number x, whatever it was, that number between 1 and negative 1. Or if we have arc-cos as our outer function, the arc-cos of the cos, those are going to cancel, and we're going to be left with y, whatever angle y was. It has to be some angle between 0 and pi radians. Now the last one is arctan, and we learned yesterday that arctan, just like arcsine, is defined in quadrants 1 and 4. But the difference here is arctan, for x values, we can plug in any real number. We could plug in a number between negative infinity and positive infinity. Any number can go in for x. Y has to be between positive and negative a half pi. If those conditions are met, then the tan of the arctan will cancel, and our answer is just that number x. If we have the arctan of the tan, those will cancel, and whatever this angle y is, that's our final solution. Y again has to be between negative half pi and positive half pi. So let's peek down here below that properties box. It says, keep in mind, these inverse properties do not apply for any arbitrary values of x and y. You know, it's sort of like a trap. If I put this on a homework worksheet or a test, some students might see the arcsine of the sine and think, okay, those are going to cancel out, and my answer is going to be 3 pi over 2. But our answer is not going to be 3 pi over 2. So how do we figure out what this answer is? Again, arcsine and sine are not going to cancel, and our answer is not going to be 3/2 pi. There's two ways we can look at this. We can look at this inner function first. Here we have the sine of 3 pi over 2. If you look at your unit circle, you know 3 pi over 2 is going to be down here. 3 pi over 2 radians. The point on the y-axis would be 0, negative 1. So we want the sine of that angle. Of course, the sine is the y-coordinate, so that value is negative 1. So we could replace this with a negative 1 and then say, well, the arcsine of negative 1. What is the arcsine of negative 1? Well, we'd go back to our unit circle, remembering that we're only defined in quadrants 1 and 2. Where is sine equal to negative 1? Well, that's going to be down here. That point again is 0, negative 1. How do we get there? What angle opens up to give us that value? Remember, we're only defined in quadrants 1 and 2, so we can't go around the unit circle. We got to take the clockwise or direct route. And if we go in this direction, that's going to be negative pi over 2. So our answer is going to be negative pi over 2, not 3 pi over 2. Very, very different answers there. 3 pi over 2 is way wrong. Pi over 2 is correct. Another way I guess you could look at this, you know, we have the arcsine of the sine. This angle, 3 pi over 2. Remember, arcsine is only defined between positive and negative half pi. Or I guess they use the letter y for this, so I should stay consistent. The angle must be between positive and negative a half pi. Well, if I look at the unit circle, and I find that angle 3 pi over 2. You know, on the unit circle, that is a quadrant angle. This is 3 pi over 2. Well, you could just say to yourself, okay, I want to, you know, get down here, but I know I can't go around through quadrants 2 or 3, so I have to take the clockwise or the direct negative route to get there. And to get there, instead of 3 pi over 2, I could call this negative half pi. So now if we go back to the original problem, you know, I'm looking right here. Let me write it below. The arcsine of, oops, that's a terrible parenthesis, of the sine of 3 pi over 2. You know, what we did is looked at the unit circle, and we just found a different way to write this angle. I can rewrite 3 pi over 2 as negative pi over 2. Now I can say the arc sine. Why does it keep doing that? The arc sine of the sine of this angle. I did it again. Oh, nice and slow. There we go. So now this angle, this value here, is between positive and negative a half pi. So we can just cancel out the arc sine of the sine. And that answer is just going to be negative pi over 2. And it does say below, in other words, the property, the arc sine of the sine of y equals y, is not valid for values of y that are outside of that interval from positive to negative half pi, quadrant 1 and quadrant 4. Okay, let's try some of these out here. Okay, the first one, we got the tan of the arctan of negative 5. Remember, we can plug any number we want from negative to positive infinity into arctan. So this negative 5 is perfectly legal. The tan and the arctan are going to cancel. So our answer is just negative 5. All right, letter B. The arc sine of the sine of 5 pi over 3. Now remember, arc sine, we can only plug in numbers in between positive and negative pi over 2. I guess I should use a y there. Why not? So does this angle, 5 pi over 3, fit in there? No, not at all. 5 pi over 3 is 1 2/3 pi. That's definitely outside of this range. So there's two ways to do this. We could look up the sine of 5 pi over 3. And I have a unit circle right here. So let's see, 5 pi over 3 is down here. The sine value down here is this y coordinate. We could replace those parentheses with negative root 3 over 2. So I could rewrite this as the arc sine of the sine, the arc sine of this sine of 5 pi over 3. We said that is equal to negative root 3 over 2. So I could replace that with a negative root of 3 over 2. And now can we find the arc sine of that value? Well, I'm going to slide my unit circle over here because we know we are only defined in the first and the fourth quadrants. Where is our sine value? Negative root 3 over 2. Well, it's right here. And that happens at this angle. But remember, we have to take the clockwise or the more direct negative root to get there. And that's going to happen, we open up an angle this way. That's going to be negative pi over 3. So that's one way to look at that problem. Another way, and I think this might be the simpler way, would be this. We realize that 5 pi over 3 is out of our interval from negative to positive a half pi. So we go right to the unit circle. We find that 5/3 pi. And then we just find our root. We don't want to go around through the quadrants we're not defined in. We just want to go this way. And we already established that's negative pi over 3. So I could rewrite this as the arc sine of the sine, and I'm replacing 5 pi over 3 with negative pi over 3. So now our angle is in the interval, positive to negative a half pi. Sine and arc sine will invert each other away, and our answer is just negative pi over 3. Now, letter C is also kind of a little tricky one. If we look at that, as a lot of you, as soon as you see that pi, you're going to think that's an angle. That's pi radians. But remember, what do we put in to inverse functions? Do we put angles in them, or do we put numbers in them? We put numbers into inverse function, and angles come out. So this pi is not an angle. Think about that as 3.14. We want to do the cos of the cos inverse of the number 3.14. Can we do that? Remember, the numbers that go into cos inverse are x values between negative 1 and 1. 3.14 is definitely outside of that interval. So for this letter C, that is not possible. We can't do it. We can't put a number that big into the arc cosine function. Remember, numbers go into inverts and out come angles. So this we cannot do. That pi is not the angle pi radians. It's the number 3.14. So be careful. Some of this, the test is going to be short, but it doesn't mean it's easy. Take your time. Think through this stuff. Okay, example 6, we're going to do some compositions of functions, but now if you look at them, they're different functions. Here's the tan of the arc cos. And letter B, the cos of the arc sine. Oh no, I bet this is going to be horrible and hard and very, very difficult to learn. Actually, it's not. Okay, we're going to start, of course, with the inner function. Our inner function says arc cos 2/3. So we know we have some angle. And what they gave us here, this 2/3, that's two sides of the triangle. If you want to think about it this way, this might make it clearer for some of you. If I write x equals the arc cos of 2/3, and I'm going to do something to both sides of the equation. I'm going to take the cos of the left side, the cos of x. And when I take the cos of the right side, the cos and the arc cos will cancel. So we're just left with the 2/3. So this is saying the cos of x, or I should have wrote theta because I'm using theta here. The cos of theta is 2/3. This 2/3 is two sides of the triangle. Cosine is what two sides? Well, SOHCAHTOA, cosine is adjacent over hypotenuse. So I know my adjacent side to angle theta is a 2. I know my hypotenuse is a 3. Okay. So we use the inner function to set up our triangle. But we're missing a side. We're going to have to find that side. Pythagoras to the rescue. A squared plus b squared equals c squared. Or, that's a terrible 2. Leg squared plus leg squared equals hypotenuse squared. Or 4 plus b squared equals 9. And we subtract 4 from both sides. B squared is equal to 5. And then we square root. B is the square root of 5. Square root of 5. So that's this missing side. Okay, we're almost home free. This hasn't been too hard so far. So we use the inner function to set up our triangle. Pythagoras gave us the missing side. Now we want to evaluate the tangent of that same angle. So what is the tangent of this angle theta? Well, tangent is opposite over adjacent. Root 5 over adjacent side 2. Root 5 over 2, that's our final answer. The tangent of the arc cos of 2/3 is root 5 over 2. Okay, on to letter B. Last one here for example 6. Now I notice this one, it's negative, and it's saying the arc sine is negative. So what quadrant are we in? If arc sine is negative, we only have quadrants 1 and 4 to choose from. Everything is positive in quadrant 1, so we have to be in quadrant 4. So I'm going to flip my triangle around so it looks like this, because here's my xy axes. This would be 1, this would be quadrant 2, here's 3. So we are in quadrant 4, and this will be our angle theta. And they're telling us the arc sine is negative 3/5. So sine is opposite over hypotenuse. The opposite side is going to be 3. The hypotenuse is going to be 5. But the question is, which of those is negative? If you remember back to section 8, it was either 6/1 or 6/2. I think it was 6/2 when we did the trig function of any angle. When we set up these triangles in the coordinate plane, hypotenuse was never, never, ever negative. So by default, the 3 has to be negative. Or if you think about being in the fourth quadrant, if you were to graph this point in the fourth quadrant, as we counted out along the positive x-axis, these would be positive numbers. But as we dip down here below the x-axis, we would be in negative y-axis territory. That makes this y-coordinate a negative value, so this side is a side of length, where you could call it negative 3. Its length isn't negative 3, its value is negative 3. So we have this negative 3, we have our hypotenuse is 5. Hopefully you remember a 3 blank 5 triangle. This has got to be a 4. Our missing side is a 4. Or you could do Pythagoras. Negative 3 squared, negative 3 in parentheses, negative 3 squared plus b squared equals 5 squared. If you solve that, you'll get b squared is 16, and the square root of that is 4. So there's our missing side 4. Now we want to evaluate the cos of that same theta. The cos of theta, SOHCAHTOA, tells us that will be adjacent over hypotenuse. Adjacent's 4, hypotenuse 5, so our final answer is 4/5. And the show's over. The cos of the arc sine of negative 3/5 is equal to 4/5. Okay, that's where the book examples end. But in the homework, there's a batch of questions. I believe in your notes, I named this example 7. You know, there's a batch of homework problems similar to this one. The book did not have an example in the text of it, so I'm going to use this problem 48 as our example. So we read the directions, of course. Use an inverse trig function to write theta as a function of x. That's the key right there. Write theta as a function of x. And what that means is when we solve this, when we're all done, we want to have theta equals something. And in that something will be the variable x. Write theta as a function of x means theta equals what? So we look at our triangle. We have an angle marked theta. We have two sides. So from the perspective of the angle, what sides do we have? We have the opposite side and we have the adjacent side. So what trig function deals with opposite and adjacent? Well, we are forced to use tangent. The tangent of theta is the opposite side, x minus 1, divided by the adjacent side, x squared minus 1. We're almost home. We want theta equals something. We have tan of theta equals something. How do we get rid of this tangent? Of course, we tan inverse. We tan inverse here, those cancel. So we're left with theta equals, well, we got to also tan inverse here. It's only fair. The tan inverse of this quantity, why does it keep doing that? The tan inverse of x minus 1 divided by x squared minus 1. There's our final answer. Theta is written in terms of x. Alrighty, practice time, huddle problem time. 43 is like the one we just did. 49, that's the sign of the arc sign, be careful. 56 is the secant of the arc sign, so set up the triangle and then, find the missing side and evaluate it. So pause the video, try the problems, start her back up, and see how you did. Alrighty, let's check this out. 43. We have an angle. Oop, there we are. We have an angle. We have the opposite side. We have the adjacent. So just like the example, this is going to be the tangent. The tangent of angle theta is the opposite side, x over 4. We want to write theta as a function of x, so we're going to tan inverse the left side to get rid of tan. And that means we have to be fair and tan inverse, or you could write arctan, of that x over 4. And we're done. Okay, number 49. Was it a trap? Did I try to trick you? Well, we're doing the arc sign, so we're putting a number into arc sign. This number must be between 1 and negative 1. 0.3 does fall in there, so the sign and the arc sign will cancel, and our final answer is 0.3. And the show is over. All right, last one, number 56. A composed two different trig functions. The inner function will set up our triangle. The arc sign 4/5. So they're telling us sine and 4/5. We have two sides of the triangle. If I call this my angle theta, sine is opposite over hypotenuse. Opposite is 4, hypotenuse is 5. Ooh, look at that. We got a what 4-5 triangle. It's got to be a 3-4-5. Pythagoras would also verify that result. Now here's where we got a little twist. Secant. Secant is not part of SOHCAHTOA, but secant is the reciprocal of cos. Remember, secant is 1 over cos. So what I want to do is find the cosine of theta and then flip it over to get secant. So what is the cos of theta? Well, from this angle theta's perspective, cosine is, oops, I should put that back there. Cosine is adjacent 3 over hypotenuse 5. So the cos of theta is 3/5. What does that make the secant, what we were really looking for? The secant of theta will then be 5/3. And there we go. Homework for this section, 6.6 day 3, that's page 516, these problems. The odd ones, again, check them in the back of the book. The even ones, be a little extra careful with. Those answers are not in the back of the book, and those are the ones I really, really look at when I'm grading the homework.